In this module, we will start our discussion with some advanced problems of dimensional synthesis. We have already discussed three-position synthesis of four-link mechanisms, namely for motion generation, path generation, and function generation. We have already seen that using these three problems and a two-stage synthesis technique, we could have designed first a slider crank function generator and then use that design to generate an approximate straight line path generation of a 4R linkage coupler curve, which could be coordinated with the input, that is the crank movement. Today we will start our discussion with the design of a 6-link forklifter with only revolute pairs. As we know, these forklifters are used in industries to shift article from one place on the shop floor to another place, but such forklifters normally have two vertical guides or two prismatic pairs. But we all know that the prismatic pairs are difficult to maintain and more costly to manufacture. There is more friction also in the prismatic pair, whereas revolute pairs are easy to fabricate and there is virtually no maintenance, and because of rollers, that is the revolute pairs with the pin and hole joint, there is hardly any friction because the pin diameters are normally not very large. Let me first show you the model of this proposed 6-link forklifter with only R pairs. This is the model of that proposed 6-link mechanism to be used as a forklifter consisting of only revolute pairs. As we see, there are the body of the truck is the fixed link or link number 1, then there is link number 2, 3, 4, 5 and 6. And as this input link of the crank is moved by a motor, what we see, that fork, that is this link number 6, moves up and down almost vertically. But this vertical movement is without any vertical guide. We will try to design this problem such that these two fixed pivots are located on the body of the truck at convenient positions, and we have to come up with this link length such that the rotation of the crank is converted into almost vertical movement of this fork. We will solve this problem by what we call a multi-stage synthesis. Let me now pose the problem with the required design specifications. Let us now discuss the details of the design of this 6-link forklifter with only revolute pairs, the model of which we have just now seen. We will achieve this design by a process which we can call a multi-stage synthesis. That means the techniques that we have already learned for path generation, motion generation and function generation will be applied in a number of stages to get to the final design. The design specification, for example, in this particular mechanism, let us represent it to the following parameters. First is the 60-degree rotation of the input link should cause 1.5 meter vertical travel of the fork. That means as the input link crank rotates through a 60 degree, the fork should travel along a vertical line, almost along a vertical line through a distance of 1.5 meter. Not only that, the travel of the fork should be proportional to the input rotation. As we know, we cannot have the vertical line exactly vertical at all configurations, and we go through what we call a precision point approach. And we decide to use 3 Chebyshev's accuracy points during this entire travel of 1.5 meter. At this stage, let me now go back to the sketch of this mechanism and define the other parameters. Let me now refer to the proposed sketch of this forklifter. These two fixed points O2 and O4 are to be placed on the body of the truck at convenient locations. These 2 points B and D belong to the fork, and the BD defines the fork completely. And we want that 60-degree rotation of this input link should cause 1.5 meter travel along this vertical line. So we start the design assuming a convenient location of O2 and a vertical line in front of the truck where I want the line BD to move. Let BI represents the initial point of B and BF the final point of B on this vertical line. So BI to BF, this distance is 1.5 meter, and the corresponding rotation of this input link should be 60 degree. Now first step is to determine the three Chebyshev's accuracy points in this range BI to BF, which we shall call B1, B2 and B3. The three Chebyshev accuracy points in this interval from BI to BF can be determined, as we know, both analytically and graphically. First of all, let me determine these three accuracy points B1, B2, B3 analytically. We have been given the delta S, that is the total movement, is 1.5 meter. We are going for three Chebyshev's accuracy points, that is n equal to 3. A, that is the distance of the midpoint from BI, is delta S by 2, which is 0.75 meter with the origin at BI. The interval, half of the interval H is also delta S by 2, so again H is comes out as 0.75 meter. Then the three accuracy points Sj, with J going from 1, 2 and 3 can be obtained from the formula as 0.1005 meter, 0.75 meter and 1.3995 meter. Let me now obtain the same 3 points B1, B2, B3 graphically. To determine the three accuracy points graphically, let me refer to this figure. This is the initial point BI, which I have chosen on this chosen vertical line, and this is the point BF, and to this scale BI to BF, this delta S is 1.5 meter, and we have to locate three accuracy points from in this range BI to BF graphically. To do that, first we draw a semicircle with BI BF as diameter. This is a semicircle with BI BF as diameter. Because n is equal to 3, so I now draw a regular hexagon with two of its sides perpendicular to this diameter and inscribed in this circle. The half of this hexagon is shown the half of this regular hexagon is shown. This hexagon is inscribed within this circle. So the projection of these three vertices 1, 2 and 3 onto this diameter BI BF locates three accuracy points, namely B1, B2 and B3. So B1, B2 that is the travel of the fork we represent by S12. Similarly, B2, B3 the travel of the fork from the second to the third accuracy point is what I call S2, 3. So S12, S23 is now known. I can either measure it from this diagram to the scale, or I have already calculated analytically. The second requirement is that the travel of this fork should be proportional to the rotation of this input link of the crank O2A. So we calculate what is the corresponding movement of this link 2, which I call theta 2, 1, 2 and theta 2, 2, 3. Now we have decided the 3 accuracy points corresponding to the fork point B, namely at B1, B2, B3, both analytically and graphically. And we have got S12, that is S2 minus S1, as 0.6495 meter analytically, and in the drawing we got it to some scale. And S23 is exactly same, because the rotation of the crank has to be proportional to the movement of the fork. The relationship is theta 2, 1, 2 divided by S12 is same as delta theta by delta S, where delta theta represents the total travel of the crank and delta S represents the total travel of the fork. Because now we are trying to design O2AB as a slider crank, where B is the location of the slider and O2A is the crank. So delta theta is given as 60 degree and delta S is given as 1.5 meter. So from this relation, because S12 is known, we can find theta 2, 1, 2, which turns out to be 26 degree counterclockwise, and theta 2, 3 again is 26 degree counterclockwise. So in the first stage of the synthesis, the problem boils down to designing a slider crank O2AB such that the sliding movement at the slider positioned at B is coordinated with the rotation of the crank O2A according to this relation. That 26 degree counterclockwise rotation of the crank should produce 0.6495 meter vertical travel of the slider. Further 26 degree rotation in the counterclockwise direction of the crank will again cause further 0.6495 meter vertical travel of the slider. So let me now at the first stage design the slider crank mechanism, which I will now explain through the usual graphical method which we have learned earlier. So at the first stage of this synthesis problem, let me start B1, B2, B3. These are the 3 accuracy points corresponding to the slider movement at B. We choose O2 arbitrarily, and the whole problem right now is a function generation problem as the slider crank, such that this downward movement from B1 to B2, which is 0.6495 meter, should occur during 26 degree rotation of the crank in the counterclockwise direction. Further 26 degree rotation of the crank will make the point B2 to come up to B3. This we have already learned how to do this. We choose O2 at a convenient location on the body of the truck. We have chosen this line conveniently at the front of the truck, and I have located B1, B2, B3 according to Chebyshev's pressure. We apply the method of inversion. We hold the crank fixed at its first position, and the crank pin at A1 has to be located. Here we have already drawn the solution, but my objective is to locate the required point A1 such that the slider crank O2AB acts as a function generator. If we hold the crank fixed, then we know this O2B2 has to be rotated through 26 degree, but in the clockwise direction. So we rotate B2 with O2 as center. This line O2B2 is rotated by 26 degree, and this point we call B2 inverted on the first position, or B21. Because we are holding the first position fixed, the inverted position of B3 I can get by rotating O2B3 by 52 degree. This line O2B3 is rotated through 52 degree, and we get the inverted position of B3, which we call B31. This is B31, this is B21, and this is B1, which is same as B11. Then A1 has to be at the center of the circle, passing through B11, B21, and B31. To determine that, we do the usual simple geometric procedure. We draw the mid-normal of B2, B1, B31, which is this line. This is the mid-normal of B21, B31, and we also draw the mid-normal of B11 and B21. This is the line B11, B21, and we draw the perpendicular bisector of this line, and these two lines intersect at A1. So finally, at the end of the first stage, we have designed a slider crank mechanism, namely O2 A1 B1, where A1 is the crank pin, such that I know the 26 degree counterclockwise rotation of this crank will cause the slider to come from B1 to B2. Further 26 degree counterclockwise rotation of the crank will cause the slider to come from B2 to B3. In the next stage, we will get to a 4-bar linkage such that I can remove the slider, and this coupler point B1 will automatically pass through B1, B2, and B3 when that 4-bar linkage is moved. But that is the second stage of the synthesis. So in the first stage, we have obtained this O2 A1 B1. Now I remove the slider at B1 and treat this link AB as the coupler of a 4-bar link, namely O2 AC04, and B is the coupler point of this 4-bar link O2 AC04. Our objective is, how do I determine the correct location of O4, so that when this 4-bar linkage is moved, this point B1 will automatically pass through B1, B2, B3, and maintaining the coordination with the input movement. This problem we have solved earlier, so without elaborating, let me say I choose C1 somewhere in the middle range of this AB, not too close to A, not too close to B, but somewhere in this middle region. So I have chosen C1. Now when this slider crank goes from O2 A1 B1 to O2 A2 B2, C1 goes to C2. I draw A1 goes to A2, that is 26 degree, B1 to B2, that is 0.6495 meter, and I get O2 A2 B2. Because this length is already fixed, so from A2 I measure this length and get to C2. So I locate the point C1. Similarly, in the third configuration O2 A3 B3, I find the corresponding location of C and I call it C3. Then I can always draw a circle through these 3 points, namely C1, C2, C3, and the center of this circle is at O4. The center can be easily determined by drawing the mid-normal of C1, C2, which is this line, and the mid-normal of C2, C3, which is this line, and these two lines intersect at O4, determining the required location of the fixed hinge O4. The point to note that because I choose C1 somewhat arbitrarily, I have no control over the location of O4. Here it happens to be within the boundary of this struck body, but with a different choice of C1, this O4 could have been very much away from the body of the truck, and then we had to do more iteration such that with a proper choice of C1 only, I can get O4 in a convenient location. So at this stage, that is at the end of the second stage, I have got to a 4-bar linkage, namely O2AC04, such that when this 4-bar link moves, this coupler point B1 has the desired movement and is also coordinated with the input movement. At the second stage, I do it a little differently, because as I have seen that with an improper choice of C1, O4 can go to an inconvenient position. So the second method, what we will do, I will choose rather O4 conveniently at the body of the truck and try to locate the required C1 on this coupler link AB. So in this alternative procedure, we say that O2 A1 B1, O2 A2 B2, and O2 A3 B3 are already known to us. Instead of choosing C1, I rather choose O4 conveniently on the body of the truck, say at this location, which we call O4. Now, to determine the point C1 on the coupler link, I make a kinematic inversion holding the coupler fixed at its first configuration and obtain the inverted position of O4. As we know, because this C belongs to the coupler and CO4 does not change, so if we hold the coupler fixed at its first location, this point O4 will move on a circle. To obtain the inverted position of O4, we follow the usual procedure. We mark A2, B2 and O4. These are the relative positions of A2, B2 and O4. Because the link AB is not moving, when I make a kinematic inversion, I take this A2 and B2 to coincide with A1 and B1 respectively. So I move, if you remember, this point represents B2, this point represents A2, and this cross represents O4. And they define the relative position of A, B and O4 at the second configuration. Kinematic inversion means this relative position should not change, though I am not allowing AB to move from A1, B1. So I move this tracing paper, A2 coinciding with A1, B2 coinciding with B1, and wherever O4 goes, that point I mark by piercing on this tracing paper and mark this point as O4 2, 1, because it is the second position of O4 inverted onto the first position. Following the same logic, I also obtain the inverted position of the third configuration. That is, on the tracing paper, I mark A3, B3 and O4. These are the relative positions, but inverting on the first position, A3, B3 coincides with A1 and B1 respectively. And wherever O4 goes, it has come here, that point I call O4, 3, 1. So this way we have obtained the 3 inverted position of O4, which is same as O4 1 1, O4 2 1 and O4 3 1. Now if I draw a circle passing through these 3 inverted positions, then the center of that circle will be C1. So as usual, I draw the perpendicular bisector of this line and the perpendicular bisector of this line. These two bisectors meet at the point C1, determining this revolute pair on the coupler link at C1. So now I have got a different 4-bar linkage, namely O2, A1, C1, O4, with B1 as the coupler point, which will pass through B1, B2, B3, maintaining the coordinated movement with the input link. So here the location of O4 is convenient, but as we see, the coupler has become not a very lean member, but a heavier member, triangular in shape. Previously the coupler was almost a straight link, and now this coupler has become triangular in shape, but we have control over the fixed hinge O4 that I can choose conveniently on the body of the truck. So at the end of the second stage, either following the previous procedure or this alternative procedure, I can get to this 4-bar linkage with the coupler point movement coordinated with the input link. In the third stage, I will convert this to a 6-link mechanism such that BD, which is not seen here, BD will be my fork of the lifter. So at the end of the second stage of the synthesis, we have determined A1, C1. We had already chosen O2, O4 and this vertical line on which I had B1, B2 and B3. But if this fork is hinged at only one point, this will be swinging like a pendulum. So to guide this fork vertically, I choose another convenient point D1. This is chosen arbitrarily. Now B is at B1, D is at D1. When at the second configuration, when B goes to B2, because this distance remains same, I can locate D2 and similarly D3 corresponding to the third position on the same vertical line. The only task is to determine this revolute pair on this link at E1 such that D1 passes through D1, D2 and D3. To determine this E1, I make again a kinematic inversion keeping this link fixed, that is the follower link of this O2AC04, this 4-bar linkage. The follower link I hold fixed at its first position and determine the inverted positions of D1, generating the same relative movement but holding this link 4 fixed. So at the second stage of our synthesis, we have determined this linkage O2, A1, C1, O4, out of which O2 and O4 had been chosen conveniently on the body of the truck. The line of travel of the fork was also conveniently chosen in the front of the truck, and we have come up to this design O2, A1, C1, B1 and O4. As we see, this fork, if it is hinged only at one point, it will swing like a pendulum. So to guide the fork along this vertical path, I choose another point which I call D1, which I choose conveniently on the fork. And now this point D1 with a revolute pair has to be connected to this link 4, that is O4C1, such that D1 goes through D2 and D3. This distance BD remains same, so from B2 I can locate D2 on this vertical line and D3 also on this vertical line. So I have got D1, D2 and D3. To locate the position of E1, that is this revolute pair on link number 4, again I apply the method of inversion holding this link, that is link number 4, O4C, fixed at its first configuration, and determine where is D21 and where is D31. To do this, we follow the same method of kinematic inversion. this is D2, this is O4, and this is C1. Sorry, this is C2. So I mark O4, C2 and D2. Now I am holding this link O4C fixed at its first position. So what I do, I make C2 coincide with C1 and O4 does not move. And wherever D1 goes, that becomes my D21. Let me repeat. To get the inverted position corresponding to the second configuration, inverted on the first position, I mark O4, C2 and D2. Since O4C is not moving from the first configuration, I make O4C2 coinciding with O4C1. That is, C2 coincides with C1, O4 coincides with O4, and wherever this D2 moves, that I call D21. Similarly, to obtain D31, I mark O4, C3 and D3. Now, holding the link 4 fixed at its first position, I make O4 at O4, C3 at C1, and wherever D3 moves, that I call D31. Since link 4 is fixed at its first position, this link length is of constant length, so E1 can be located at the center of the circle passing through D1, which is same as D11, D21 and D31. So again, following the usual technique, I find the perpendicular bisector of these two inverted positions, D21 and D31, and the perpendicular bisector of D11 and D21, which is given by this line. These two lines intersect at E1, determining the location of this revolute pair on link 4, and I connect E1 and D1 by a rigid link. If we do not allow this link to move, then obviously D1 goes on a circle with E1 as center. So E1 is determined at the center of the circle passing through D11, D21 and D31. So at this stage, I have finished the design of a 6-link mechanism which gives me a fork lifter where the fork goes almost vertically. At least it passes through B1, B2, B3, and the point D passes through D1, D2, D3, lying on this vertical line. Of course, there will be deviation a little bit as it goes from B1 to B2 from this vertical configuration. But the deviation is not much, and it acts as a very good fork lifter, particularly if the load is not heavy, where the movement of the fork has been coordinated with the rotation of the crank, and the fork goes almost vertically, and we end up getting a fork lifter without any vertical guide. Let me now summarize this multi-thread synthesis of this guideless fork lifter as we have completed in today's lecture. We have chosen first O2. This is this fixed pivot at a convenient location of the body of the truck. We have also chosen a vertical line in front of the truck which is convenient for the movement of the fork. So first we design O2AB as a slider crank such that the slider movement at B is coordinated with the input motion of the crank. 60-degree counterclockwise rotation of the crank has caused 1.5 meter vertical travel of this point B using 3 Chebyshev accuracy points in this interval. Next, we chose O4 conveniently on the body of the truck. Then removed the slider and got a coupler point here at C such that O2, A, C, O4, this 4R link has a coupler point B which has an approximate straight line path, and the movement along that straight line path is coordinated with the motion of the input crank. In the third stage, we had chosen this point D again conveniently on the body of the fork, such that a second point is guided along the same vertical path. After choosing this point D, we found the inverted positions of the D corresponding to the second and third configuration, holding this link, that is link number 4, fixed at its first configuration. And the center of the circle passing through these three inverted positions of D, namely D11, D21 and D31, I found the center of that circle at this point, which I called E. Finally, we get this 6-link mechanism where I have a forklifter without any vertical guide. So the techniques that we have learned for function generation, motion generation and path generation can be synthesized together to have a multi-stage synthesis problem for even more complicated problem. So in today's lecture, we have designed a 6-link forklifter using only revolute pairs by a multi-stage synthesis process, which are basically combination of the 3-position synthesis for function, motion and path generation of 4-link mechanisms, which we had discussed earlier. In our next lecture, we will try to design another 6-link mechanism for a rail-less garage door, a garage door which will be opening inside the garage rather than coming out of the garage, and in the open position it will become horizontal to the roof of the garage, using again only revolute pairs and not using any prismatic pair.